Let's review the equilibrium constant. The equilibrium constant K is derived from the law of mass action. For the reaction shown, the equilibrium constant is written as the product of the products raised to the power of their coefficients divided by the product of the reactants raised to the power of their coefficients. For reactions in solution, when reactants and products are given in molarity, we write the equilibrium constant as K sub C. For gaseous reactions, when reactants and products are given in atmospheres, we often use K sub P. But you can see that any time we write an equilibrium constant, we write products raised to their powers of the coefficients divided by reactants raised to the powers of their coefficients. Let's make a few points about the value of K. And here, in this picture, I've just called it KEQ. In other words, it could be K sub C, it could be K sub P. It's just a generic equilibrium constant. K is independent of initial concentrations. It varies with the temperature, and it's written with no units. Points about the equilibrium constant expression, which is this whole thing. It's the equilibrium constant K, and it's also the products over the reactants. The equilibrium constant expression never includes pure liquids or solids, only gases and substances in solution, and it depends only on the reaction stoichiometry. That is, you can write the equilibrium constant expression directly from the balanced equation. For this gaseous reaction, let's write the K sub C and K sub P expressions. An equilibrium constant is products raised to their powers divided by reactants raised to their powers. In this case, we have one product, and the power of its coefficient is 2. So for the K sub C, again C stands for concentration, so we write square brackets, and then we raise that to the second power. We divide that by the concentration of NO raised to the second power, and the concentration of O2 raised just to the first power. K sub P, which we can write for any gaseous reaction, is very similar, except instead of using the square brackets, which imply concentration or molarity, we use a capital P for the partial pressures, but you can see that the expressions are very similar. If we're asked to do the same thing for this reaction equation, which is simply the reaction equation at the top of the screen run backwards, we're going to get K sub C and K sub P expressions that are exactly the reciprocals of the top of the screen. This stresses the point that when writing an equilibrium constant expression, we must refer to a specific reaction equation. And however the equation appears, that will dictate how our equilibrium constant expression looks. The K's for the forward and reverse reactions are not the same. They're reciprocals. You can see the two boxes that are light blue in color. In the top one, we've got NO2 squared in the numerator and NO squared and O2 in the denominator. If you look at the other blue box, the NO2 concentration squared is in the denominator, the NO concentration squared and the O2 concentration are in the numerator. And same thing for the green boxes. So let's write the equilibrium constant expression for K sub C for this reaction. We note here that we have some solids that are in the reaction. This tin 4 oxide and this tin are solids. Solids and liquids do not appear in an equilibrium constant expression. The only things that appear are gases or things in solution. So the carbon dioxide is going to appear raised to the power of its coefficient, and the carbon monoxide, which is on the reactant side, is going to appear in the denominator raised to the power of its coefficient. If the equation that we were given instead looked like this, again, the pure solids are left off, the gases are included, and we raise them to the power of the coefficients that are shown in the equation. In other words, the equation dictates what our equilibrium constant expression is going to look like. Now, of course, these are the same reaction. Tin 4 oxide reacting with carbon monoxide to form tin and carbon dioxide. Both of these reactions, they're exactly the same reaction. But the way the equation is shown has told us how we need to write our equilibrium constant expression. Let's talk about the magnitude of the equilibrium constant. If K is much, much larger than 1, that must mean we have a lot of product and comparatively little reactant. When that's the case, we've got lots of product, and we say products are favored, and that the equilibrium lies to the right. The right side is where the products are. If K is much, much smaller than 1, then clearly we must have a lot of reactants and not very many products. So if we fill in these blanks, we're going to say we have lots of reactant, and we say reactants are favored, and that the equilibrium lies to the left. Let's summarize. 1. The equilibrium constant expression is written directly from the reaction equation, with the products in the numerator and the reactants in the denominator. We never write the formulas for solids or liquids, only for gases and things in solution in equilibrium constant expressions. 2. The equilibrium constant K has no units. In addition, because K values vary with temperature, whenever a numerical value of K is reported, we should state the temperature for which that K value is valid. 3. When K is large, there is a large concentration of products at equilibrium. When K is small, there is a large concentration of reactants at equilibrium.